All right, this is the last video for chapter 16. We've been looking at nuclear chemistry, and this one we're going to take it a little step further. We're going to look at two other applications, nuclear fission and fusion, and then we're going to also look at just some of the effects and some of the uses of radioactivity and radiation. All right, let's get going. First, just a couple big picture things. All right, so you've probably heard of the words fission and fusion. Just to make sure we get them straight, kind of consider them kind of opposite to each other. Fission is breaking up of a large nuclei into smaller pieces. All right, and then fusion, okay, you're fusing things together. Smaller nuclei coming together to form one. Both of these, energy is released. All right, so there's a lot of energy at play here in both fusion and in fission. All right, we can see that Einstein's equation there equals mc squared, and we've looked at that a little bit in some of the earlier videos. All right, so let's look at them a little bit more closely, starting with fission. All right, so nuclear fission is the type of the reaction that's carried out in nuclear reactors, okay, and this is to generate nuclear energy. You can see coming in, you have a neutron that has to start this off, and it bombards a very large uranium nucleus. And what it does then is causes this nucleus to split into two other smaller, okay, daughter atoms here. So you have a krypton and a barium. In the process, it also releases more neutrons. All right, so it took one neutron in, and now you have made three more. All right, and if you kind of think of this process, if one neutron comes in and now you make more, and then those neutrons hit other large nuclei, and then they make more neutrons, you can see this kind of continue on and on. This is what we call a nuclear chain reaction. And this is what is happening when you have nuclear power or if you have a nuclear bomb. Let's look a little bit more at the nuclear power part here. So here's a nuclear reactor. You will have heat that is generated. Okay, this releases a lot of energy in the form of heat, and this then will be able to then heat up some steam, and that steam, just like we've seen with other ways of generating electricity, turns this turbine, which then will generate electricity for you. So here you want to just make note, here is the core. Okay, this is where your radioactive isotope are. Okay, and so this is going on here. It's a closed system. It releases a lot of heat. That then has this other system that will heat this, cause steam, and then that goes on to turn the turbine there. Couple things to note. The U.S. is using probably about 22% is the most recent thing that I saw of its power from nuclear power, and it's great. It's a nice closed system here. All right, so your nuclear material should not get out at all. Okay, it's all closed. However, the thing you want to worry about is there could be some release of radioactive material when you're trying to store this and trying to keep it safe, because the uranium will decay, and we looked at that whole series of decay. And so you can then make more and more, which takes a lot of time. Some of these half-lives are really long. So you're going to have leftover, not useful radioactive material that you now have to keep safe and store. So that's one of those worries. People might be concerned about nuclear explosion occurring. They keep this core pretty well organized, right? If the more neutrons you have, the reaction just kind of takes off, a chain reaction. But if you can have something that absorbs some of those neutrons, and these are the control rods, they will absorb neutrons so that you don't get to that critical mass where then you have uncontrolled nuclear reactions taking place. All right, so this is fission, a great way to generate. Okay, you're not burning coal and releasing some stuff like other ways of generating electricity. So, you know, for the most part, it's considered a fairly clean way to generate power. Let's look at fusion now. So fusion is what occurs naturally in the stars, especially in our sun. So this is very high temperature. And it happens by combining of small nuclei. So hydrogen atoms can combine to form a helium atom. So here's kind of an image of this occurring right here. this is a great way to generate power because the products here are not radioactive. So you don't have any of the issues with, oh no, now we've generated products that are radioactive we have to take care of. You're not generating those. So here's just a helium and a neutron. So why aren't we using this? Well, the main problem is it requires really, really high temperatures. This material must be in the plasma state at several millions of Kelvin. So super high temperature. You can't have anything that even can hold this for this reaction to take place. So it happens in the sun and the stars. On Earth, we can get it to happen in a nuclear bomb. So nuclear bomb, you use like a uranium or a fission reaction, okay, to take place, which gets it to super high temperature, which then inside there you have hydrogen, which then could make that hydrogen bond. So the heat from the nuclear bomb sets off this hydrogen bond of fusion. So that's that would be a great way to figure out, if we can get the next couple of years to be able to figure out how to really figure out how fusion can work and how we can actually make this a way of generating power would be amazing. All right, let's look a little bit more now at some of the biological effects. So we've looked at fusion and fission and how to use those. Let's just look at some of the biological effects. So the thing you want to be worried about when you think about radiation is ionizing radiation. So this is where you have enough energy to break bonds. Okay, so here's ionizing radiation. Here is a bond between a nitrogen and carbon. And now you have broken this bond. You've made a radical, you've lost an electron, and you have a cation, some more unstable things that they can now go attack. So this is something you want to worry about. I think I have another picture that's going to show up. Let's see. There we go. We can see some of these particles. So here's the alpha, beta, and a gamma ray. And this kind of shows you, okay, not all ionization or radiation is equal to each other. An alpha particle, since it's so heavy, it doesn't really go through much. So you can block an alpha particle with a piece of paper. A beta particle, being smaller, can go through paper. It would be blocked by aluminum. And then the gamma, we know that's high in energy, no mass, so that can go through lots of stuff. You have to be careful. And that doesn't mean, when I say alpha and beta are not as dangerous, that's true outside the body. But if you get them into somehow, if you're emitting or if you ingest them at all or get them into your body, sometimes we do this on purpose, but if they're in there, now they have closer contact with any tissue, so then they do become more dangerous. So that's kind of thinking about the different types and how powerful they are. We put this to use in the medical industry, all right? So nuclear procedures are used in medicine, okay? They're very helpful. You can have things trying to break down tumors, all right? Areas that might not work with other types of drugs or treatments might be able to get affected by having a gamma ray at the tumor, okay? You want to direct it right at the tumor and no other areas, but you could then try to break down a tumor that way. Just being able to image things is very helpful to make a good diagnosis. So imaging is useful in using nuclear isotopes for that. Analyzing things in your blood, okay, and you can see here is a whole list of various radioisotopes that are used in some of their uses. So you can see things like PET scans and cancer therapy, brain scans, the iodine-123 we mentioned earlier with thyroid therapy as well. So that's the medical, and I want to also leave you a little bit with other applications besides medical. Irradiated foods, okay, and medical equipment. Instead of having to clean medical equipment with like some type of bleach or other thing, you want to be able to kill the germs and disinfect it. And this is one way to do it. Also with foods, it keeps it from spoiling. And the food itself doesn't not turn radioactive. It's not radioactive, it's just been hit with the radioactive decay particles to help kill any germs that would be present, bacteria from growing. You can also use radioactive activity is used in the agricultural industry. All right, so improving food production and packaging. You're exposed to it with safety all the time, even if you don't know it. Radioactive reflective signs have been treated. Also smoke detectors. While you're sleeping, radioactivity is helping you sleep a little bit more peacefully. This uses americanum 241 is the isotope there, and it has a little bit of the decay continues on, except if smoke gets in there. So if there's a fire and there's smoke, that separates the ions from being able to move and then sets the alarm off. So smoke detectors, even using measuring amount of air whipped in our ice cream, measuring thickness of paper products. There are so many different uses that radioactive isotopes have been used, and they're all good to make our life better. So don't be scared when you hear the word radioactive. Just make sure that you're informed. You now know about the different types of decay. We've talked about some of the great uses of radioactive decay, and we're going to stop with that. There we go. We have finished chapter 16.